Welcome to the 13th lecture video for Physics 4C. Having introduced the Lorentz transformation in the last lecture, we explore a few conceptually challenging scenarios, sometimes referred to as special relativity paradoxes. As you will hear me say in the lecture, there are no true special relativity paradoxes, quote-unquote, in the sense of actual logical contradictions. What we call special relativity paradoxes are simply this: scenarios that challenge our classical intuition, built in a world where light didn't always travel at speed c, and any two simultaneous events could be said to be simultaneous in absolute time. You will see that the resolution of many special relativity paradoxes will come down to identifying the moments in time, or rather events, that we thought were simultaneous, but really weren't. Or usually they were simultaneous in one inertial reference frame, but not simultaneous in another inertial reference frame, where we thought we were getting a paradox. So, in this lecture, we will cover the twin paradox, the ladder paradox, sometimes called hole in the barn paradox, the time dilation paradox, and a scenario from Tipler's textbook called PHYS paradox. In all these examples, you will see the use of space-time diagram as a disambiguating tool, clearly showing world lines of different objects and illustrating which events are simultaneous in which reference frame. Next week, we will finally start on the practical aspects, for future particle physicists anyway, of special relativity, studying the dynamics and interactions of particles that are moving at relativistic speeds.
So this is a way of kind of visualizing what I was drawing by hand here. So let me do first with the time dilation, since that's kind of easier to see. So some of the things that are being illustrated here, so right now the relative velocity is 0, so both reference frames have the perpendicular x and time axis. And this red dot is marking a point, an event in space-time. And so you have some time coordinate there. And when you imagine looking at this as a reference frame that's moving relative to I guess where this event is happening at the same location as x equal to 0. The blue dot that you see, it represents the moving of the clock. So imagine, this is what you're comparing. We have a clock that's going to count down 1, 2, 3, 4 seconds. Good? And the clock is going to start moving relative to you. And you're still going to look at how long does it take for it to count down 4 seconds. And if you are looking at the clock moving relative to you at, I don't know, half the speed of light, you'll find that even then the effect is not that great. So if it's moving at half the speed of light relative to you, then let me do this grid line. Sorry, a lot of grid lines here. So the red grid line is the one at rest, the lab frame. And the blue grid line is still showing, 1, 2, 3, 4 seconds that the clock is counting. And the red grid line is now showing, okay, it doesn't quite take 4 seconds. It takes 4.7 or 4.8 seconds. So this is for something that's moving at half the speed of light. And you can quite understand why people didn't notice this effect before. Like, if something is moving at 10% of speed of light, is that a lot? Is that moving pretty fast? 10% of speed of light? Yeah, so speed of light is 300 million meters per second. 10% is still 30 million meters per second. We don't have anything that moves that fast, short of small particles. We don't have any spaceships that move that fast. And when you look at that, it's like the effect is almost unmeasurable. But once it's at half the speed of light, then the effect is measurable. and close enough to half. And when it's at, I don't know, so there's no limit. As the speed of light gets close to 1, or as this fraction gets close to 1, the time dilation can, it's a question of how large can gamma be as beta approaches 1. Infinity is the limit, right? To this time dilation factor, well, infinity is the limit. It's as large as you can make it. All right, so that's for time. So for time dilation, it's quite simple. Nothing, at least for now, nothing appears paradoxical. I'll mention something that will point out the paradox a little bit more clearly. Let's have you look at length contraction. So this is the length contraction picture. Oh, I guess maybe before I say anything, let me just try this. All right, that's good enough. So this is, the red is the stationary ruler, and the blue is going to be the moving ruler. And let's say you are trying to take a picture of each ruler at time equals 0, at t prime equal to 0. Yeah? Then, the red ruler is sort of, red ruler is what it appears as at t equals 0. And if you took a picture of the moving ruler at t prime equal to 0 and represented on this space-time diagram, this is how it would, so right now it's at rest, so it appears exactly the same. Let's say it's moving at half the speed of light. If it's moving at half the speed of light, then this is what it should look like. The picture of the moving ruler that you took, so at t prime, so you take the picture. Let's say you have a guy who's moving with the ruler, and you ask him very carefully, at t prime equal to 0, please take a picture, or please flash the ruler so that you can see how the flash, and then you can see those spots of light as the ruler is being illuminated all at once at t prime equal to 0. In your own reference frame, this is what you would see. You would see one end of the ruler illuminated before, and then over time, the rest of the ruler illuminated. The guy who was moving with the ruler didn't make a mistake. From his reference frame, it was simultaneous. But from your reference frame, because simultaneity is relative, it's not. And so if you are measuring these two positions, then you would see that as, well, that's longer than my ruler. This position here, this position here, that's longer than my ruler, but that's not the correct interpretation. It's because like measuring this point and then later this point, it doesn't constitute a length measurement in your reference frame. In your reference frame, you have to wait for this point to come down here, and so you have to measure them both ends at the you have to measure both ends simultaneously. So that means measuring this end at this time and measuring this end at this time. And when I bring the grid lines back, then from when this was at rest it was at something close to, I don't know. Okay, close to 2 or 2 grid lines, and as it's moving, you will see those red dots. That's the length measurement in your reference frame, getting shorter and shorter. Once again, without limit, can be. Although this you will never see with the macroscopic objects because we don't have spaceships going at 99% of speed of light. So yeah, so this is the visual illustration, and I will tell you that this is so special relativity didn't make a lot of sense to me until I saw space-time diagram. That's really my biggest complaint against Giancoli, which used to be our textbook, that it doesn't treat space-time diagram. Last year, when I taught this class for the first time, I excerpted the chapters from a textbook called the Tipler, which is actually pretty good for special relativity and modern quantum mechanics. But I don't want to make you pay $200 to just buy that book. So I will write up a note for the space-time diagram. What I want to illustrate right now in the few minutes I have is how to use this space-time diagram to explain some of the paradoxes in special relativity. So let me actually ask you about a paradox that I think more people find easier to resolve. Let me describe it and see if any of you have an answer. So this is the description of a very well-known paradox called twin paradox. So imagine this hypothetical situation. You have two twins, Alice and Bob. They are fraternal twins. So at 18th birthday of Alice and Bob, who do you want to be the astronaut, Alice or Bob? Let's say Alice, okay. Alice travels to, I don't know, Sirius, which I'm going to pretend is 10 light years away. It's probably something close to 10 light years. Sirius, 10 light years away. That travels to sets off, and immediately after reaching Sirius, I'm just gonna say S, reaching Sirius, returns to Earth. And let's say she's moving pretty fast. She's on a spaceship that's moving at, I don't know, 80% of speed of light. So this is the question. When Alice comes back, who's older? So when Alice comes back, is Bob older or is Alice older? Let me have you consider this question for maybe a minute, and I will just poll the class which one people thought should be the case. Because when they come back and you compare their ages, one of the two is probably going to be older. From what we know about time dilation, something about the passage of time will be different for somebody. And I want to figure out, so who's older? Okay. So give you 30 more seconds, and then talk to your neighbor if you want to. You have 30 more seconds. And I'll just poll the whole class. So I find the majority of people get the answer intuitively correct. So, well, let's see. How many people say Bob is the twin that's going to be older? Okay. How many think Alice should be the twin that's going to be older? Okay. So the correct answer is yes. Bob is actually older. Now, that's not the paradox. That's kind of easy to, well, maybe not that, whatever. Most people get that, and it doesn't confuse a lot of people that Bob should be older. It's the explaining this part. It's trying to explain the whole thing from Alice's perspective. So yeah, so from Bob's situation, you see that Bob sees that Alice's clock is running slower. So Bob sees Alice getting younger and younger as he ages. Oh, sorry. So let me calculate some numbers I'm going to need. So traveling at this speed, traveling round trip of 20 light years, the total time of duration is, wait. I can divide by 5 to multiply. Wait, no, that's not how it works. Sorry. 20 light years total, divide by 4/5. So it's going to take the total of 25 years, right? Yes? Okay. So as Bob ages from 18 to 43, Bob sees Alice not getting as old as he is. So when Alice comes back, Bob, 43-year-old Bob looks at Alice who's much younger, 30-something or something. Now, the paradox is this. How do you explain it from Alice's perspective? So Alice sitting in his spaceship, who's moving? Is Alice moving or is Bob moving? Bob is moving. So as Alice moves away, Alice is seeing Bob getting younger than she is, because she's aging normally from her own reference frame, but she looks back at Bob, who's moving backward from her, and she's saying, oh, my twin Bob is getting younger than I am. Is this situation any different on the return trip? Also, on the return trip, does Alice see Bob aging faster than she is? Look at the expression carefully. So this expression for time dilation, it involves gamma, right? Gamma only involves the square of velocity. So it doesn't really depend on the direction of speed. As Alice is moving away and moving back towards Bob, it's the same picture. So on the return trip also, Alice sees Bob as aging less than she is. So if this is going to be correct, at what point did Bob age faster than Alice did, from Alice's perspective? So that's the paradox, and that, I mean, you can explain it in some intuitive level. I guess one way of presenting this paradox is that the situation is symmetrical. And when you draw it on space-time diagram, you will see that, oh wait, this doesn't have the twin paradox thing. Let me just do it this way. Let's say, so Alice is moving at speed of, so 80 or 0.8 speed of light. So once you diagram what's going on a space-time diagram, then it becomes easier to see because this is what you are seeing. Let's say that the unprimed coordinate is Bob's reference frame, and the primed coordinate is Alice's reference frame. So this is Earth. Let's say Sirius is somewhere here. This is Sirius. So Alice reaches Sirius here. And then upon reaching Sirius, so Alice travels to this point here. And upon reaching that point, she comes back at the same point, same speed. So something like, I don't know, so 2.5. So she comes back to Earth at this point. So this is the trajectory of Earth, or you could say this is the trajectory of Bob, who stays on Earth. So once you draw this picture of the journey, Alice's journey and Bob's journey, then you can immediately see that it's not symmetric at all, right? For Bob, who stayed on Earth, he remained in one inertial reference frame the whole time. For Alice, she was in one inertial reference frame as she was moving away. And somehow, as she switches inertial reference frame, that's where these two are no longer symmetric, and you could more easily justify why you could. So in saying that Bob is older, you are essentially saying that Bob's reference frame is the correct reference frame. Alice's reference frame is the wrong reference frame. Yes? That sounds okay to you? And so I think a lot of these people can figure out if you think about long enough, even without the space-time diagram. But what the space-time diagram is good for is explaining exactly how Alice's reference frame is wrong. And this is what this comes down to. I said this on the first day, that most of the paradoxes with the special relativity comes down to misunderstanding about simultaneity. Okay? So it's about the sense of right now. So as Alice is moving away from Bob, so let me draw the, let me replot the axis. That's going to plot Alice's sense of right now. So sorry, it's going to be very cluttered. But you see these blue lines? You see these blue lines? Sorry, you see these blue lines here that's parallel to the x-axis, x prime axis. That's what represents Alice's sense of right now. So when Alice is here, Alice's sense of right now is here. So when Alice looks at Bob, this is where this is the, so this is, it's a lot easier to imagine, not sorry, when Alice observes Bob. So easiest way to explain this, imagine Alice as a magic telescope, which can break the speed of light barrier. It can just let you look at whatever things look like right now. And that's what you would have if you have the reconstructed observation. So Alice has a magic telescope which lets her look at what Bob is doing right now. And this is what Alice would see Bob doing right now as she's arriving at Sirius. Okay? And you can see that for her, the time of, I can really see, time of something like a year or unit and a half has passed. And for Bob, only unit of 1 has passed. So yes, Alice does see Bob as younger. And this is what you can show on the space-time diagram. So you can show it with this particular program. But so as something was moving to your right, the axis changed this way, right? If something's moving to your left, how do you think the axis changes? The other way, right? So the t prime, so this is actually what represents the t prime axis as Alice is returning. And what looks like the x prime axis, it'll look, so let's see. If this is the, so this is the, if this is the line representing speed of light travel, then the x prime axis would be this one. This is the x prime axis. So as she was arriving at Sirius, this was Bob right now. As she's leaving Sirius, this is Bob right now. So Bob time skips a bunch of years as Alice is turning around. And now this turning around, that would take some finite amount of time. So in reality, something can just turn around on a dime, like, that would require infinite acceleration. Her real trajectory might look something rounded like this. But during the time of acceleration, Bob skips this number of years. So that period of acceleration is when Bob got older than Alice. But for the rest of the return trip, Bob is still not aging as fast as Alice is from Alice's perspective.
So with that, let me just quickly state Lorentz transformation and its relationship to space-time diagrams. So this is how I like to always specify Lorentz transformation. I kind of want to do it in terms of two relatively newly defined variables. One of them is beta. It's speed in the unit of speed of light, V over C. So beta is a unitless quantity, and it's useful because it's it makes some of the formulas simpler. I think that's the most useful way in which it shows. In fact, the very first formula it simplifies is the Lorentz factor gamma, which you have seen last week. Gamma is in terms of beta, it can be written as 1 over square root of 1 minus beta squared. And the value of gamma also is that it simplifies some of the formulas. So when you write down Lorentz transformation, which is a rule that tells us how to express or how to figure out what the coordinates in the primed coordinate system are. And as a quick description of what this priming means, you have to imagine two inertial reference frames. One inertial reference frame that is at rest. You might call this quote-unquote lab frame. This is what you maybe think of as rest frame. And you can think of a second inertial reference frame. It's inertial in that it's not accelerating. It's moving at some constant speed. And this other inertial reference frame could be defined by a vehicle or something that's moving at some speed beta c relative to the lab frame, and this would be our primed coordinate system. And we are imagining, okay, let's take a point here, and that point can be described in terms of the time and space coordinates in the lab frame. It would have a time coordinate in the lab frame, and it would have some kind of space coordinate. And this same point here can be represented in the time and the space coordinates that refer to this moving inertial reference frame. So that's what Lorentz transformation describes. It tells you how to get these primed frame coordinates if you know the unprimed frame coordinates. Let me write that down. So, so y and g are the simplest. They don't change at all. Y prime is just y. G prime is just the g. So this is where this is moving in the plus x direction. And the how the x prime coordinate transforms, it actually makes a lot of sense if you connect it to how Galilean transformation would look like. So actually the Galilean transformation would look like x minus beta ct, beta c being the speed at which this frame moves, and t is the amount of time. The only real difference between Galilean transformation and Lorentz transformation is this presence of vector gamma. Or, if you're putting this into divided by square root of 1 minus beta squared. But we define this vector gamma so that our expressions will be simpler. And it turns out it has a lot of uses, so we'll keep it. The hardest is really the time coordinate. And this is the one that I don't really want to have to derive. So I'll just state what it is and point out the symmetry between the transformation of the space coordinate with the time coordinate. So the time coordinate transforms this way. There's still this gamma factor here, and there's the time portion, ct. And then it has a second term that you never would have expected from Galilean or Newtonian physics. There's a minus beta x. Sometimes we say in Lorentz transformation, the time and space coordinates mix, as in space coordinates come into determining some of the time coordinates under this transformation. So that's a Lorentz transformation. It's something that you are going to be seeing a lot in the next couple weeks. And so this is the short, really abbreviated version of the introduction. We do have a longer intro in the other recorded lectures. Now, Lorentz transformation is algebraic, and there's an aspect of it that's kind of difficult to gain understanding of quickly. One especially is the relativity of simultaneity. And Lorentz transformation actually includes that. This line here, actually, if you think through it carefully, it tells you right away that simultaneity is not relative, because a set of points that have t is equal to 0 do not necessarily have the same property that t prime is equal to 0 because of this space component getting mixed in. So Lorentz transformation already includes those important concepts, but it doesn't make it manifestly evident. So the graphical tool that I like to use, which frankly for me was revolutionary in helping me understand special relativity, is what we call space-time diagram. And I was showing earlier the 15-minute video covering introduction of space-time diagram and demonstrating some of its uses. So here I will just limit to drawing what it looks like and what it illustrates. So what it looks like a kind of an XY graph. The only thing that's different is what the axis represents. In an XY graph, The x represents a horizontal axis, y represents a vertical axis. What more is there? With the space-time diagram, the horizontal axis traditionally represents x, one of the dimensions of position, and the vertical axis or the vertical-ish axis represents time, ct. And the most important thing that space-time, so this is a kind of a blank canvas where you can represent motion of a particle, for example. You can plot as a function of time, its position at all times. It's one of the things you can do. And what this ends up being very useful for is for illustrating Lorentz transformation. So um, so so in this picture here, let me draw the axis that represents the axis for the space-time coordinate of the S prime frame. I think before I draw that, it'll be useful for me to draw this particular line, which you could call light world line. It's trajectory of light in space-time. It has slope 1 because of the way we are plotting the y and the x-axis. And this is useful for as a kind of a reference line. So if you imagine this container is moving at an appreciable fraction of speed of light, let's say, I don't know, 20% of speed of light, then this is what the space-time axis within that frame would look like. This is going to be the CT prime axis. And this is going to be the X prime axis. And I think a CT prime axis is easy to understand. It's the set of points where x is equal to 0, or sorry, x prime is equal to 0. So it's, let's say, whichever point within the vehicle you said is x prime equals 0. This is showing how that point moves in the reference frame of the lab frame. That kind of, we had something similar in Galilean relativity. I think this is pretty easy for us to comprehend. What takes a lot of intuition building is this axis, the x prime axis. What does it mean? How does it relate to other things? And what graphically, what this x prime axis out to mean is this. These are set of points where ct prime is equal to 0. They all have the same value of ct prime. And in fact, in the lecture for space-time diagram, that's what I do. Set ct prime here equal to 0, and then derive an expression for line. And what this means is that this is what someone might call line of simultaneity. These are the set of points that represent everything in the reference frame S prime that would be happening at t prime equals 0. So this illustration alone shows that what's considered to be simultaneous in the S prime frame is different from what's considered to be simultaneous in S frame. So in this drawing, the simultaneity in S frame looks like a horizontal line, and any other horizontal line would connect to simultaneous events. Now, in the S prime frame, this is what defines things that are simultaneous. So two events, for example, one here, that were simultaneous in the lab frame, they are not simultaneous in the S prime frame. In fact, this happens earlier. The time coordinate for this is less than 0. And any other line of simultaneity, if you draw it, it would be parallel to this ct prime is equal to a 0 line. So this is the point where ct, it's later than what you have at the origin. This is the line that represents points that were earlier before the origin. So that's the quick as quick as I can make it. A quick introduction to Lorentz transformation and space-time diagram. And what this is useful for is for analyzing situations that when you hear the description of, seems quite unintuitive, maybe even self-contradictory. And that's where the description paradox comes from. And I want to caution you that when we say special relativity paradox, it's not really paradox in the mathematical sense. That's why I keep putting the scare quotes, because this is what I like to say. The special relativity has no paradoxes, just situations that are difficult to understand at first. But once you understand it, it's all logically consistent. There's no contradiction anywhere. This is not like Russell's paradox or I don't know any other paradoxes. There are genuine paradoxes in mathematics where two things actually contradict each other. Like what is it? A liar's paradox. A statement like this statement is a lie is a self-contradicting paradox, because if the statement this statement is a lie is true, then the statement should be a lie. But and if it is a lie, then which means it's a true statement, so it's not a lie. That's what a real logical paradox is. And the special relativity paradoxes, they are more of a confusing situation where without a intuition for special relativity, you would think there's something that self-contradictory, but once you learn to understand it, then there's nothing paradoxical about it. So as I was saying before we got into this, I do cover some of these paradoxes already in the available lecture. And I think one of the classic paradoxes that I haven't covered is something called Paul in a barn paradox. Wonder if your textbook does. I probably should have checked if it does. If it does, then I will do it in the context of the text, what textbook already does. Paul in the barn paradox. Let me just put in the word barn. No, so your textbook might not. So let me just do that. This is a fun paradox situation to think about. And even though the phrase "Paul in the barn" paradox is a common name for this paradox, let me just demonstrate that with a Google search. Paul in the barn paradox. I'm gonna give or I guess ladder paradox. I'm gonna use a slightly different situation, because we have been using the setup of train and train station already. So let me just continue using that. So I will call this train in train station or train in station paradox. And I'll put quotation around the paradox just to emphasize that it's not real paradox. It's just something that you need to understand. Once you understand it, there's nothing paradoxical about it. And I guess I can state this particular paradox in this way. Let me give some concrete length so that we are not dealing with abstract. So let's say we have a train of length. Let's make the length easy for me. I'm going to say it has a length of 10 meters. Let's say whenever we specify length, we mean proper length. So I won't have to specify that it's a train's proper length. I'll just say that it's a train's length. And by saying that it's train's length, it's understood that this number just it's measured in the train's rest frame. So it's a proper length. So I have a 10-meter long train. It's a fairly it is a really short train. It's a fairly short train that's moving at some relativistic speed. Let me make this a relativistic speed easy for me. I'm going to say it's I'm remembering 0.866 c. I think that it's supposed to be a fraction if it's meant to be exact. I'll just leave it here. But I have a relativistic speed train that's moving at that speed, and it's approaching a train station. And I want to see if this train will fit between two gates of that train station. So this train is coming towards the train station. Um, and let's see, how long do I want to make the gates? Let me make this easy at first. So I'll say that the two gates at the station are set up so that they will close at the same time, and they are separated by 10 meters apart. So the length between the gates is 10 meters. So the question is, so between the train conductor and the station chief, they are trying to arrange all this so that as the train passes by, they're gonna close the gates, and then I guess you have to open the gates again. Otherwise, the train's gonna just bust through the one of the gates. So, but the goal here is to just close the gates, measure the length of the train, or do something meaningful, and then open it again. Um, and as you are doing this, you have a disagreement between Alice, the train operator, and Bob, the station chief. Bob claims that there's a plenty of space here. The train, which is a moving ruler, is short. It's a Lorentz contracted. So Bob says that as the train passes by, he's going to able to fit the train actually well within the length of the length between the gates. I think if I worked out the Lorentz contraction factor right, this Lorentz contracted length will actually be about 5 meters. So that's what Bob claims that he'll be able to do. But from Alice's perspective, it looks different, because from Alice's perspective, it looks like the station is approaching towards her train, and from her perspective, these gates will be contracted. So these gates won't quite be separated enough to be able to contain her train. So that's the paradox. Who is right? Is the train able to fit between the two gates, or is it not? Shouldn't it be one or the other? Um, so that's the paradox. And I think this is the paradox that's harder to resolve than the twin paradox, because at least with the twin paradox, a lot of people get a sense of some kind of closure, an answer that one twin gets older, and the younger twin is younger because that younger traveling twin is changing reference frames. And in this paradox, you don't even have that. You just have two reference frames moving relative to each other. And the statement sounds so reasonable, train either fits or it doesn't fit. So which is it? This is the kind of paradox that I felt really I understood once I learned to analyze it using space-time diagram. So let me give you a description of this setup with space-time diagram. So let me draw a space-time diagram axis here to illustrate this paradox with. And I'm drawing it so that I have more space on the plus side of both CT and X. And I feel like it'll be useful for me to have a light world line reference, just so that I know how to angle my other stuff. All right. Let's say this unprimed coordinate, this is the station. And we'll draw as necessary the axis for the train. I guess, in fact, I might as well do it now. So drawing it, so I've done the introduction of how to draw these axes in the space-time diagram lecture, 25-minute lecture. I'll just do it here. So my CT prime axis, which I can define my coordinate axis so that it matches up with one of the ends of the train. The back of the train, let me make that match up with x prime equals 0. That'll make the world line of the back of the train match up with the ct prime axis that I need to draw. So I'm not quite drawing it to scale because I think if v equals 0.866 is rather extreme value, but this should be close to ct prime. And the slope for this, if I drew it properly, the slope should be 1 over beta. That's how it should be. And the x prime axis, that's the axis defined by setting ct prime equal to 0, or in the Lorentz transformation, that should look something like this. And as your textbook was describing, when done properly, this angle here is same as this angle. It kind of scissors in to how the Lorentz transformation axis looks like. So that's the reference frame of the train. And the slope of this, if you draw it correctly, it should look like a beta. That's what the slope here looks like. Okay, so space-time diagram axis, that sets the setting, the stage. And what it is for stage 4 is I need to now draw the world lines of the object. So I think I've already drawn the world line of the back of the train. So let me draw the world line of the front of the train. So let's say from here to somewhere around here, that's 10 meters in the x prime axis. So my front of the train here is going to at least have a point here. And the front of the train moves at the same speed that the back of the train does. So if I draw the world line, the trajectory of the front of the train, it's going to have a slope that's the same as my back of the train. If I'm drawing this line right, these two should look kind of parallel. All right, that seems good enough. So this is the front of the train, and this would be the back of the train. And let me try to set up my coordinate axis so that we are trying to close the gate when the back of the train aligns with the behind the left side gate. So that's where our t is equal to 0 will be, and at t equals 0, that's when the back of the gate is right at the, or back of the train is right at the gate, and the front of the gate, it should be, let's see here. So I'm just eyeballing the scale. I think the scale should be around here, should be the 10-meter length for the 10-meter length in the station frame. So let me draw the world lines of these gates. So the back gate, the left side gate here, it's gonna be at x equals 0, and it's just gonna stay there for all time. It basically, the world line for this basically goes along the ct axis. Kind of boring. It's just a vertical line, maintaining the same x value forever. And actually the same thing for the right side gate. Yeah, let me just keep using red. So the right side gate is at 10-meter position, stays there forever. So it's gonna look something like, again, I'm kind of eyeballing it, so I'm not doing the scale 100% right. I think I've actually drawn it a little bit too far to the right. It should have been a little bit farther to the left. So, okay, I think I have illustrated everything. Now that I have drawn everything, I think I can now, I'm now in the position to explain this training station paradox. Let me first describe the Bob, the station chief's perspective. So Bob, the station chief, closes the gate at t equals 0. So at t equals 0, he closes the gate. So the event, the space-time coordinate at which he closed the gates, they can be represented by these 2 points. This point here, the back of the left-hand gate at t equals 0, and this point here, the right-hand gate at t equals 0. And what he finds the train to be doing at that time is he finds that the train is occupying this space here at t equals 0. So he says, oh, yeah, the train has Lorentz contracted. It fits well within between my gates. From Alice, the train conductor's perspective, this is what Alice says. You have to understand that Alice does not see these two events as being simultaneous in her reference frame. In fact, this is a line of simultaneity that describes the set of points that are simultaneous in her reference frame at t prime equal to 0. Uh, There is another line of simultaneity that goes through this point, but it would have to be parallel to the x prime axis. And this is some distance below the x prime coordinate. So there is a value of ct prime that's associated with this. It's something less than 0. It happens at some time before this point does. So from Alice's perspective, this is what it looks like. As her train passes by, she sees that the station chief closed the right gate first and then opened it. And then at some later time, as the back of her train was going through the right gate, that's when he closes the right gate and then opens again. So from Alice's perspective, the train never fit between these two gates, closing and opening, because one gate closed and opened well before, um, at one point in time, at this point in time, and the other gate closed and opened at a much later point in time. From Alice's perspective, at the space-time coordinates that are simultaneous to her, if she were to mark some spots, I don't know, maybe drop a bag or something, then she would be marking these 2 points as being simultaneous in her reference frame. So this is the back of the train, that's fine. That occurs at the same time as the gate closing and opening. And this is the front of her train at t prime equals 0. And that at t prime equals 0, she's seeing this gate is already, it's Lorentz contracted. So the front of the train is already past the right side of the gate, right gate. So at that t prime equals 0, that Alice doesn't see that the train fits into the station. And if we were to try to do something to mark these positions, I was saying, okay, maybe Alice can drop a bag as she's passing by the station. So she drops a bag at x equals 0, and she drops a bag here. And from Bob's perspective, what this would look like is Alice would drop a bag at the back of her train as that passes through the right gate, but she doesn't drop her front bag at the same time. She actually waits until a later time when the front of the train has passed through the gate and then drops a bag. So from Bob's perspective, Alice cheated because she didn't drop the bags at the same time. So this is where relativity of simultaneity matters. When we say at the same time, it really should have either quotation mark, or we should specify at the same time in what reference frame. The space-time diagram clearly shows in what reference frame it is at the same time in. So anything that's occurring at the same time in the station reference frame would be connected by horizontal line. anything that's happening at the same time in the train's reference frame would be connected by a line that has a slope of beta. So that's the explanation of one of the paradoxes, the training station paradox, using space-time diagram.
Okay, welcome back. I want to talk a little bit about one more paradox to sort of reinforce what we talked about with the twin paradox, because here, it's all kind of artificial, complicated, maybe, and the point of confusion can get buried in all that. So I think this is really the simplest picture where I can highlight the paradox and the origin of the paradox again. So some textbooks, probably not ours or Giancoli, would cover this as the time dilation paradox. And I want to be clear here, the paradox is not the time dilation effect. I think, from our experiment and our postulates of special relativity, we feel comfortable with the Lorentz transformation, and we feel comfortable with this as the effect of the Lorentz transformation. So this is not the paradox. So let me describe the paradox. Imagine you have two clocks that are identical, like this clock and let's say this clock. They are more or less identical. Right now, when they are in the same reference frame, they are ticking down the same amount of time. So imagine Alice and Bob. Let's say this time Alice is staying with the left frame clock, and Bob is taking this clock and zooming by. As Bob zooms by, Alice looks at Bob's clock, and in the time it takes, in the amount of time it takes for this clock to count down 1 second, does Alice's clock count more than 1 second or less than 1 second? So this clock, moving clock, takes 1 second of time to count down. What does Alice's clock measure? More than or less than a second? More than? More than a second, right? That's the time dilation. Moving clocks are slow, so in the time it takes for this to count down 1 second, that clock counts down more than a second. So that, so far so good. There's no paradox there. The paradox results in when you try to shift to your reference frame. When you imagine you are Bob, you are taking the clock, you are moving by. In the time this clock takes 1 second to count down, or in the time it takes this clock to count down 1 second, how many seconds have your clock counted down? More than a second or less than a second? A lot of people say less because you feel uncomfortable saying that, because you are implicitly answering this question, which of the two clocks are slower? And in the earlier description, we said that this clock is slower. So you want to stick with that. You want to say that as Bob is moving, in the time that this takes a second, in the amount of time it takes this to count down 1 second, you want to say this will count down less than a second so that this will keeping a slow clock. And I will tell you the correct answer is that from Bob's reference frame, that is the moving clock. So that moving clock is slower, not this stationary clock. So that's the paradox. Time dilation is symmetric. When you have two clocks that are moving relative to each other, whatever clock in its own reference frame will measure the other clock as being slower. It's quite paradoxical when you think about it, because it's like saying, A is less than, if I wrote down this, A is less than B and B is less than A, this would be logical contradiction. And that's what paradox is. What I will tell you is that this is the quote-unquote paradox, because this seeming contradiction, it's only a result of your flawed intuition. So let me show you better mathematically how this comparing of two clocks looks like. This is really difficult to explain in words. So this is where space-time diagram really helps. So let me do that. Let me draw the space-time diagram. So this is my lab frame. So this would be Alice's reference frame. And this time, I guess I need some kind of markers to indicate how much time is passing for Alice. So some 1, 2, 3 units, 1, 2, 3, 4 units. I'm just making some unit marker. And let me draw Bob's reference frame, which will be moving relative to this. So Bob is moving at some, let me just exaggerate this a little bit. So this is the word line for light, moving at speed of light c. So Bob will be moving at something like this. So pretty fast, but not quite at the speed of light. So if this is t prime axis for Bob, that's how fast he's moving, then the x prime axis for Bob would look something like this. Close enough. Okay? And the spacing here will actually change. That's an effect of this gamma factor here. So spacing as drawn in this reference frame from the left frame, it'll look like it's getting longer. So let me draw that. I don't know if I can draw that well. I'm just going to draw something. If they are a little bit off, forgive me. So something like this. So it'll appear to be more widely spaced because of that gamma factor. Something like that. Good. So let me describe the time interval that represents how long amount of time it takes for a clock to count down 3 seconds. So from Alice's reference frame, so this would be the Alice's clock, starting here and ending here. So this is 3 seconds for Alice, right? At the end of this 3 seconds, Alice looks over at Bob's clock at the same time. Alice observes Bob's clock at the same time when her own clock says 3 seconds. So what that's represented by is here, this point here. Good? Now, remember the distinction about observing and seeing. It takes a little bit of time for Alice to actually see it. We are reconstructing it to see, at the moment when Alice's own clock reached the 3 seconds. What was Bob's clock doing right now at that time? So, well, it's 2 and not quite 3 seconds. So yes, Bob's clock is slower. Okay? Now, let me give you, so, all this is, and I think this is where a lot of your intuition is based on. That's why more than half of you said that as Bob is moving, that Bob still sees his own clock to be slower than that, because this is the picture you are trying to enforce. Let me draw the correct, relativistically correct picture. So this is the interval that represents 3 seconds for Bob's clock. So starts at 0 here and reaches 3 seconds here. So that's 3 seconds for Bob. Now, what a lot of you are doing intuitively and incorrectly is you are looking at, 3 seconds. It's longer than 3 seconds for Alice. So so you say, so Bob's clock is slower. Right, so that's the correct answer. And Bob would look at you like a crazy person. Because to Bob, what it would look like, yeah, but you are comparing 3 seconds for my clock at a time that's significantly later for Alice. Because these 2 points are not what counts for Bob as right now. These 2 points are not simultaneous. So you have to first draw the line of simultaneity for Bob. That's the line that's going to be parallel to this line. So let me draw that line, because you have to figure out what is simultaneous for Bob. This moment in time for Bob is simultaneous. I have to draw this correctly, parallelly. So that's the parallel direction. All right. So this is the line of simultaneity for Bob. This is the line of simultaneity, by which I mean these are the set of points where t prime is equal to 3 seconds. So for Bob, at the moment when his clock hit 3 seconds, this is where Alice's clock was, less than 3 seconds. So Bob says, oh, Alice's clock is slower, which makes sense because that's the moving clock. So when Bob sees you comparing this space-time coordinate with this space-time coordinate, he's looking at you like a crazy person because like, why are you comparing those 2 points that have no meaning to me? For Bob, the 2 special points that are simultaneous are this point with that point. Now, what this point represents is this point represents when Alice would see Bob's clock strike when Alice would observe Bob's clock striking 3 seconds. That's what this point represents. But once again, that has no meaning for Bob because these 2 are not simultaneous for Bob, only for Alice. Yeah. So there's many more special relativity paradoxes that your textbook would go through, and maybe I will write up a note. But that's, I think, all we have class time for. And I will just leave you with this. This space-time diagram is the best tool there is to explore any special relativity paradoxes, because there's a lot of implicit assumptions you make when you're trying to reason them out in words. Space-time diagram, kind of like when you draw a free body diagram in analyzing forces, it makes clear a lot of the assumptions you may be making. Like once you draw this, it's clear from Bob's reference frame that these 2 points are simultaneous and these 2 points are not. It's a lot clearer than it would be in English. So this is the best tool that's available to you. And most of the so-called paradoxes, it'll trace down to you are assuming some kind of absolute simultaneity that simply doesn't exist. That's the biggest intuitive thing that you have to get rid of in special relativity. That's hard for a lot of people. I mean, with enough practice you can do it, but it's hard for a lot of people to get rid of that sense of intuition, that simultaneity is relative. Good. So this is coming out of the homework set that I had last semester. So this is, can most people read this question from where you are? Okay, let me leave it there while I erase the board and have you just think about the situation for a little bit. Makes kind of sense. Let me try to use 3-dimensional models to explain what it's trying to describe in words. So this is a special relativity paradox. Oh, I guess this kind of work. So this is approximately at the same length as this ring. And this is the situation it's describing. Imagine this ruler is moving at relativity speed horizontally. And as it's doing so, this ring is moving vertically. And they are both timed in such a way that when the middle of this comes to this origin is when the middle of this ring would also come to the origin. So the idea is that if this is going very, very slowly, so very slowly this would pass through and this would be the motion. Now, the question that's being posed is, now imagine these are relativistic. What would happen as these go through? Will this ruler pass through the ring, or will this hole kind of hit the ruler because the ruler doesn't fit anymore? I guess the motivation for this particular arrangement of situation is, so we've talked a little bit about what's sometimes called the pole in the barn paradox, right? Or train in a train station paradox. And I guess the way I've been conditioned to state it, I always stated in such a way that those moving things never come to a stop. But you will see that in many of the textbook versions, they ask the question more sloppily, as in they will ask, does the train fit in the station, or does the ladder fit in the barn, or will it crash into things and disaster ensues? And in those situations, for a successful resolution of paradox, you really should never let the ladder come to rest. Because once the ladder comes to rest, then like now the ladder and the bar are in the same reference frame. You have no relativistic effects to talk about. So this particular arrangement is a way to try to have a physically realistic scenario where you are not relying on any, you are not explicitly relying on tools of observation, like taking pictures or dropping buoys. That's in one of the past exam questions. So here, all you have are these two physical objects. And you have arranged them in such a way that this moving ruler never needs to come to a stop, and this moving kind of gate never comes to stop either. And you can kind of come to a, through analysis of this, you should be able to come to a, so there are two possibilities. Either this goes through the ring, or it gets hit by the ring. Those are two distinct physical events. And this is still special relativity, though quantum mechanics. One of those two things must happen. So the question is, well, which one of those two things happen here? Does the ruler go through the ring, or does the ring somehow hit the ruler? Let me give you some minute to think about it while I drew a copy of that here so that we can work through it, and we will work through it. Yeah, maybe 2-3 minutes. I want you to have some answer in mind and check with your neighbor if they arrived at the same answer, because I'm going to take a poll at the beginning, what you think should happen. I guess let me call it PHYS paradox. All right. So how many of you think the ruler should go through the ring, go through the hole? Like that's the physical event that happens. Okay, how many of you think the hole will now be too small for the ruler to get through, so the ruler will get hit by the hole, or the edge of the hole, rather? Some of you. Did you raise your hand for both of them? No. Okay, just the second one. All right, so let's just hear the argument. For one of the people who raised your hand on why you think ruler should be able to go through the hole, why did you think it should be able to go through the hole? Somebody who raised it. Ryan, did you raise your hand for that part? So why do you think the ruler was going to go through the hole? Okay, you think the ruler is Lorentz contracted, so it's shorter. Wait, do I have anything that's shorter than this? I don't have anything that, well, so the ruler is shorter, so now it goes through the hole even more easily. That's what you're saying, right? All right, so, and does that describe, for people who raise your hand for the first choice, is that what you're thinking, right? Yes?
I was thinking a little something different. So,
okay.
If originally, so not at relativity, if it originally does go through the hole, then it doesn't matter because the length of contraction doesn't vary in the perpendicular axis, so it stays the same. So whether it's shorter, so whether the ring gets longer as it goes up, or the ruler gets longer or shorter as it goes up.
I see. So when you say perpendicular axis, so that's why this particular example is three-dimensional.
Well, yeah, see, that's I'm not sure. I'm just thinking
yeah.
individually. So the ruler's going this way,
yeah.
and the ring goes upwards. Both don't change.
So it helps to have a reference frame in mind. So what, Kevin, you are first thinking of this situation as well. Let's compare it to when it's moving slowly first. So if that's your starting point, then the reference frame you are using is the reference frame of the axis, as in someone who's standing at the origin and just standing there. That's the reference frame you are thinking of, right? And when you said length contraction happens only in the perpendicular direction, then I think what Kevin was thinking of was for this hole, because the plane is moving up. So if there's any length contraction, that would affect the thickness of the plane, but not the size of the hole. All right, that's fine. So you're saying in this reference frame, the hole doesn't, the size of the hole doesn't change. So and if anything happen, well, something does happen with this ruler, it does get contracted along the direction it's moving. So the ruler does get shorter, right? So that's one perspective that you are using to analyze this. And when Ryan said moving rulers are shorter, that is the perspective we are considering from. From the perspective of this observer, this is the moving ruler. Yeah? Did you have something to say?
Is the ruler also going to look like it's not perpendicular, though? Is it going to look bent? Because you're going to measure one side before you measure the other side, and in between that time difference, you raised up.
Well,
so it's going to look like it's not.
It depends on the reference frame you are in. I'm thinking of this observer who's not moving here. The ruler, I think the ruler should still look parallel. Yeah, I don't see why the ruler would tilt.
Because if you're measuring both sides at different times.
Yeah, I think I see where you are getting it. You are looking at the wrong object. Let me repose the question. So most of you are thinking that the ruler should go through because you are taking the point of view of this observer, right? Let me tell you the alternate observer. What about for someone who's observing from here? Someone who's sitting at the middle of the ruler and observing in this reference frame, which is moving at the speed v. So for that person, the ruler is not a moving ruler. Ruler didn't contract. What contracts instead?
But no, it's not simultaneous.
I know, we are getting there. But what contracts? This whole contract. So it'll actually look more like an ellipsoid, or not ellipsoid, ellipse. It'll look more like ellipse. So, and that's how the whole is seen in this reference frame. And this is our goal in analyzing this and explaining. Because this is a distinct physical event, even in this reference frame, the hole does not hit the ruler. The ruler does go through. And now what we want to explain, okay, so how does it look? So that even though this hole is measurably, has a smaller major axis than the ruler, it still allows the ruler to go through. Yeah? And so let me draw the diagram. That'll probably help. And I have only 10 minutes. So I guess we won't get to the rigid body other than maybe brief mention. So your number one tool in analyzing any paradox is a space-time diagram. And so that's what I would recommend for here also, because you can talk all you want, and it's really easy to confuse yourself in flood of words. So let me draw the space-time diagram that represents this interaction as well as possible. So I'm only really going to illustrate the x-axis. And that's the thing that, let me start from there, and we will deal with the other thing later. So it's because, we only have two-dimensional space, and it's hard to, we only have two-dimensional space. So I'm taking for this axis, I'm taking the perspective of observer who's sitting at origin and then rests at the origin. And let me, I guess I don't want to be too confusing. Let me take let me draw the axis for the observer who's traveling with the ruler. So for that case, the axis would look something like this. Let me draw the light cone first so that I can draw this kind of reasonably. So the time axis tilts in this direction. Ct prime, and the x-axis tilts up in this direction. Okay? So let me start out with this, the snapshot. The snapshot where the hole is right at the origin, and the contracted ruler is right about to go through the hole, the right about to go through the non-contracted hole. This is what happens at time equals 0. Right? So for this snapshot, I need the word line of the ruler. I need the word line of the front of the ruler and the back of the ruler so that I have some marker. So those two word lines would be this time axis shifted this way by some distance and shifted this way by some distance. So, so this is the word line of the front of ruler, and this is the word line of the back of the ruler. And the Lorentz contracted length that's being measured here. What the length is? Well, the position of all the locations of the ruler at time equals 0. So this is the length contracted ruler. Okay. And at this moment in time, at t equals 0, if you are to locate 2 points, one end of the hole and the other end of the hole, the two antipodal points of the hole, then you would have, let me call this point A, call this point B. This would be A, and this would be B. Okay? So the last step is where I can't quite really draw it, because to actually illustrate it, I would need a three-dimensional space-time diagram that illustrates x-axis, y-axis, and then the time axis. Since I don't have that, let me, having drawn this to sketch out the moment in time when the ruler fits into the hole. Let me try to describe how this event appears from the perspective of this observer here. Right? So from the perspective of this observer, from the perspective of this green observer, this is what describes t prime equals 0 for him. T prime equals 0 for him, let me do that in purple, would be this. The location of the ruler here and here. So this is the picture, snapshot of t prime equals 0 for the ruler. Right? The reason this word line is helpful is knowing the location of the ruler at one point in time doesn't tell you where it was at different moments in time. And when you take snapshot in a different reference frame, what used to be simultaneous is no longer, they are no longer simultaneous. So, so I need to kind of be able to track this back. Okay, this is where it was at t prime equals 0, which will turn out to be different moment in time if I go back to my original reference frame. And so this is the ruler at this moment in time, t prime equals 0. And if you are looking strictly at the x positions, then I don't think I drew this quite right. Let me move the points A and B in so that I can represent this more correctly. So I've drawn this figure for v equals 0.5. So the gamma factor is kind of tiny here. It's not that big. It's like 1.1 something. So the points A and B are really going to be here, right? And so this is A and B. I guess I'm using the labels A and B for the event, both the position and time when it's there. So let me use a different color, orange, for the trajectory. So the one point of the edge moving up, this is one kind of trajectory in time. This is the trajectory in time. And if I sketch that in here, then the trajectory of this point, the part of the hole that was at this point, event A, looks like this. Constant x value. Right? Yes? So if you insist on the snapshot t prime equals 0, then it'll look as though this point would have hit this, and this point would have hit this. Now, physically, that doesn't happen. So if we are the observer sitting here, as you watch this hole, both moving up and coming towards you, what does this hole look like? So that as it comes, this length contracted hole, as it comes up, it doesn't hit your ruler. It looks tilted, right? The moment where this passed the, so the moment where this far end passed this positive end of the ruler, it takes a moment at this time. Let me draw this line of simultaneity to help you visualize it. This is the line of simultaneity for A. So this is x prime for A or whatever. So this lies below my x prime axis, which means this represents t prime less than 0. And this line of simultaneity that goes through this, it represents t prime greater than 0 because it's above the x prime axis. So what that means is, so this far end, it does pass the y position where this is at, but it passes it here first, and then it passes it below. So in this reference frame of the ruler, this will appear tilted. And if you want to be all mathematical, you can even go this far. You can kind of describe the y position of this as, or I guess y prime, you can describe as vy, so which will be transformed, so vy prime times t prime. And it's this value of t prime which will undergo Lorentz transformation. And even though all this happens at t equals 0, the moment where the t prime value of this, t prime here is negative, and t prime here is positive, and that's sort of described by all of this. Good? Yes? Makes sense? Yeah. So anyways, that's another example of special relativity paradox, and I just want to leave it at this level. So vast majority of you will never deal with the special relativity. Even physics majors of you, unless you go into high energy particle physics, chances are you don't really deal with the relativity all that much. But when you do see it again, this is what I want you to take away that you will remember. That it's really important that simultaneity is relative. And it's such a kind of basic part of our life that simultaneity is absolute. We tend to make a very implicit assumption about absolute simultaneity. And really drawing space-time diagram is a way to break you out of that habit, to recognize when something happens before the other. Yeah. But let me just mention this as an idea of where this paradox about rigid bodies. Let me just describe what this is. I want you to just think about this. I have a ruler, right? Let's say, imagine I'm spinning this at a particular angular velocity. I don't know. Let's say 1 radian per second. Fairly reasonable duration, right? Now, this is a meter-long thing. If I'm rotating this at 1 radian per second, what is the speed of this end point?
1 meter.
1 meter per second, right? All right. Now, can you imagine me holding a ruler that's 300 million meters long, 3 times 10 to the 8 meters, and then spinning it at the same speed of 1 radian per second? What's the speed of the end point? Speed of light. So that obviously doesn't happen, right? So where is the mistake? What went wrong? That I mean, you are applying the formula, you are familiar with this. Speed of the endpoint is the v times the angular velocity. If you don't think I can spin at 1 radian per second, then I'll make it go slower. Or I'll even take a longer amount of time so that I can kind of angularly accelerate it over a long enough period of time. So what kind of, it's a question of, well, what assumption are we making that, what assumption are we making that this doesn't actually, like the end point, it cannot move faster than speed of light. So for a very long object, very long rigid object, what would you bring in and say, this is what we thought was right, but is wrong? That's why the end point cannot move at speed faster than speed of light.
Rigid, like solid object versus
Yeah.
it like being able to bend.
Yeah, it's the assumption of rigid body. Such a thing as a perfectly rigid body does not exist in special relativity. It's a question of, what keeps it rigid? The intermolecular forces, it's electromagnetic force. Those have a kind of propagation speed limit of speed of light. So when you get, I guess let's put it this way. If I introduce a sudden change at this end, the kind of disturbance here takes the speed of sound in this material to propagate to here. And speed of sound cannot be faster than speed of light, meaning whatever change I'm making at this end takes speed of light to propagate to this end. And for extended body, what it comes down to is there's no such thing as a rigid body in special relativity. All things are not rigid in special relativity.
So actually, that goes over in for airplanes, propellers. It's for like helicopters.
Oh, yeah.
The blades actually tilt a little bit. You get that cockpit.
Yeah, and it's a material property, and there's like a maximum speed it can withstand, and yeah, before it breaks itself apart. Yeah, that's more related to the speed of sound in the material, but it's the same idea.